Hey, Dr. O here, and this is how you go about solving the for more practice problem 2.7. So the problem states that we have an electron in the sixth principal level, and it's the electron's going to relax to a lower energy level, and as it does so, it's going to emit a light with a wavelength of 93.8 nanometers, and our job is to find out what level, what orbital it relaxed into. So let me show you how I work this problem. So for any problem, the very first thing I do is I take a look at what information I'm given. And in this problem, I'm only given two pieces of information. One piece of information is that my electron is currently at the sixth principal level, and that once it relaxes, it emits a light wave with this wavelength, 93.8 nanometers. Now, believe it or not, that is enough for us to solve this problem. So we're going to be using information like this. So this tells us about the energy in the atom, the energy change of the atom as that electron goes from the one orbital down to the other orbital, and in this case it is a relaxation, so we're going from a higher orbital to a lower orbital. And then we also are going to have this formula right here where we can define energy as the as Planck's constant times the speed of light divided by that wavelength. And I put here that our job is to find the value of n, and I'm also kind of using it as n is equal to some number x. Okay, so that's how we're going to do that. Now, this is not all the information that we're going to need to utilize. We're going to have to also know the value of Planck's constant, the speed of light, and we also need to understand that the energy of the atom, once it changes due to the change in principal level of our electron, is going to be equal to the opposite value of the value of that proton. So that's the other piece of information that we are going to need to utilize. So pretty much with this, we've outlined everything that we need in order to solve this problem. Now, before we launch into solving this problem, I want to do a little something with this value right here. Because we don't use anything in nanometers, we use values that are in meters, such as the speed of light right there. So we're going to get this out of nanometers and get it into meters. And the way that we do that is we create a conversion factor. And the units that we're seeking go on top, so I'm going to put my meters on top and my nanometer on the bottom. And the thing I know about this after I looked at a chart is that 1 nanometer is equal to 10 to the -9th meters. And when I do that math, I get a value that looks like this. So I'm going to drop that value in here, and with that, I now have everything that I'm going to plug into my equations as I move forward. In the problem that was previous to this, we actually started with this information. The change in the energy of the atom is going to be equal to the basically the photon, the energy of the photon that got released when the electron went from one energy level to another energy level. So from and to, right there, I have that spelled out. But we don't have one of these values. We don't have the to value. We have the from value, but we don't have the to value. So we're going to instead use this as our starting point because we have everything we need here. We know what H and C are, and we even know what the wavelength is, so we can calculate the energy of the photon. So I'm going to start by writing that. So the energy of the photon is going to be equal to Planck's constant times the speed of light divided by the wavelength of the light that was emitted. And we're going to plug in all of those values. So there's all of our values plugged in. And I'm going to start crossing out repeating terms. So I just crossed out the seconds because I have seconds in a numerator and seconds in a denominator. And I also have meters in the numerator and denominator, and those are going to cancel out. The only units that I have left are joules, which is good because energy is measured in joules. And at this point, I just simply do the math. And when I do the math, I see that the energy of the photon was equal to 2.12 times 10 to the -18 joules. Now we found the energy of the photon, but now we have to be mindful of this equation because we want to find the change in the energy of the atom given that this photon was emitted. And the thing that we know is that the energy in the atom is the negative of the energy of the photon. So if we write our equation, then we can figure out that the energy of the atom is going to be a negative 2.12 times 10 to the negative 18th joules. And so with this information, we're going to plug this in and start solving this problem, which will eventually get us to figure out what the N is, which is tucked into this value right here. So now we're going to use this formula right here to find the change in the energy of the atom given the movement of the proton from one principal level to another one. So let's go ahead and drop that in. And the thing that I've done here is I've highlighted the value that we don't know in red because I want to isolate that on one side of the equal sign. The simplest way to do that is to add this value to both sides. So add the energy as we are in the principal level that we're moving from, add that to both sides. So I'm going to do that, and when I do, it looks like this. Now, I don't like to have my unknown on the right of the equation, mostly because when I'm doing these on PowerPoint, I have all the space over here to the right. So I'm going to flip this equation and put my unknown on the left of the equal sign and the values that I do know on the right. And then that way I can move forward. All right, let's drop in the things that we know. And we do have a value for the change of the energy of the atom when our electron went from principal level 6 down to whatever principal level. So we can drop that value in. So that's this value right up here. And then for this value, this is the formula that we're going to use, which is a negative 2.18 times 10 to the negative 18 joules over the value of the principal squared. And this is our from value, so our principal is equal to 6. Now at this point, all I want to do is solve for the math. That's all I want to do. So I'm going to do that. So the value of our energy at the second principal level, the one that the electron has relaxed into, is this number right here. Now, we can't just use this number entirely because what we did to the from value is we're going to have to do to the to value, which means that our unknown is tucked in right here. So let's go ahead and take a look at that. Now, as I was saying, we're going to have to solve the value here because in this value is where our unknown is tucked in. So we have to basically write the formula like this. So the value of our energy in the destination principal is going to be negative 2.18 times 10 to the negative 18 joules over whatever the value of that principal level is squared. And then on the right side of the equation, we can just write the value of negative 2.06 times 10 to the negative 18 joules. Now, my unknown is down here on the bottom of my fraction, and I would rather it be on the top. So the easy way to handle that is to take this value and flip it, knowing that in a minute I'm going to have to take this value and flip it too. But let's start with this one on the left of the equation sign. So when I flip this value, it's going to put my x squared on in the numerator, and it's going to put my negative 2.18 times 10 to the negative 18 joules in the denominator. So let's do that. All right, that was nice and easy. Now, if I flip one value on one side of the equation, equal sign, I have to do the same thing on the other side. So for this one, you might think, well, how do you do that? I mean, that's not a fraction. But in reality, this is a fraction. Because any value like this, any value that does not have anything in the denominator, always has 1 in the denominator. So we could basically read this as negative 2.06 times 10 to the negative 18 joules over 1. So that when we flip it, it is now 1 over negative 2.06 times 10 to the negative 18 joules. Now, when I do this, I can now multiply both sides by what's in the denominator here, this negative 2.18 times 10 to the negative 18 joules. And when I do that, this value on the left side of the equation sign goes away, and this value is now going to show up over here. So let's make that happen. Now at this point, I want to solve the math right here. I know that this is squared, but I'm not going to worry with this yet. I just want to get the math out of the way right here. So I'll tell you something. The joules cancel, The 10 to the negative 18 cancels, and all you're dividing is negative 2.18 by negative 2.06. So let's do that. So x squared equals 1.058252. So we're at a square root though, so we have to basically put this under the sign, or we're squared, which means we have to put on the square root sign, and then do that mathematical function in order to get the value of x. And when we do that, the value of x comes in at 1. This has to be a whole number. It can't be a decimal or a fraction. It has to be a whole number. So our value of x in this case is 1, which means that we went from a level 6 down to a level 1.